Yeah, so my talk today will be about the science of the aurora and how you can help. And I like to do this, but it's called a bottom line up front, just sort of what the purpose of this talk is right off the bat. So, first of all, I plan to teach you about aurora science and why it's relevant right now. And then I really invite you all to become citizen scientists and contribute your photography of the aurora to projects online to help scientists. And then, third, and probably the most important, is I really want to inspire you all to be space weather ambassadors in your own communities, and hopefully, this talk will give you some great education on the aurora, which then you can take and spread amongst all your friends and family and anyone who asks you what is the aurora. So, here's just a quick outline. First off, I'll sort of introduce myself and the topic. Then I'll delve right into what the aurora actually is, what space weather is, and how everything ties together. And then finally, I'll kick it or sort of end it all off with how to see the aurora, what is citizen science, and of course, how you can get involved. And these photos right here I took in Churchill, Manitoba in March of 2022. So if you're thinking about going to Churchill, it's right on the Hudson Bay. It's a great spot to see the aurora. Just let me know and I can definitely provide you some tips. So here's a little bit about myself. Some people call me the Aurora Guy. I was kind of given this name when I was an undergraduate student at the University of North Dakota going for my BS in physics. I took a photo of the aurora. This was in October of 2021, and the official University of North Dakota Instagram page reposted my photo, and it became their most liked photo on their page ever. And I got like 200, 300 followers, and it was a huge deal for me. And I remember all these people on campus just coming up to me and asking me if I was quote unquote that Aurora guy. And after the second or third group, my friends just started teasing me and calling me the Aurora guy. So it eventually stuck. So I'm going to run with it. But now I'm living in Fairbanks, Alaska. I'm a space physics PhD student here at the University of Alaska Fairbanks. I consider myself a professional aurora chaser. I've seen the aurora hundreds of times. It's something that I do for fun, but also I run workshops and also do Aurora tours up here as well. And I'm an intern at the Aerospace Corporation, and I'm really passionate about citizen science and science communication. I think it's really important that people know about what's really cool about space weather and how the aurora works because it's really fascinating and really just above all else, it's beautiful. So you may have heard about solar maximum, and you've probably seen the aurora this year, if not heard of all these great auroral storms and huge auroral displays we've been having. So what's really going on here? Well, here you see the plot of solar activity over the past roughly 30 years. And you can see that there's some cycles going on. These are called solar cycles. So on the y-axis, the vertical axis, you have solar activity. This is measured in sunspot numbers. So sunspots are a proxy for the sun's sort of magnetic activity. And over 11 years, it waxes and wanes in what's called the solar cycle. So right now we are at solar maximum. You can see that black arrow pointing to the current month, and we're seeing a lot of sunspots, the most sunspots we've seen in over 20 years. So solar cycle 24 peaked in around 2011 to 2013. It was a nice solar cycle, but pretty, I would say, below average. If you look at that bottom, sort of where this little shaded blue section is, you can see all the solar cycles are kind of small, but cycle 24 was a bit below average. And not all cycles are created equal. So cycle 25 is shaping up to be more of an average to maybe a little bit even above average in terms of cycle strength that we've seen since we started recording sunspots and looking at the sun over 300 years ago. So it's really exciting because not only is this year going to be great and has been great for auroral activity, but the next few years as well should be really, really good as we move through solar maximum, and then eventually we'll hit our descending phase of the solar cycle around 2028. But that just means we have a lot more auroras to come. So it's a great time to be an aurora chaser, and it's a great time to learn what the aurora is and how it works. So yeah, of course, we've seen lots of auroras this year. Here are just a few news article snippets. Down in California, they're seeing aurora, the US-Mexico border. I've seen aurora, obviously, up here in Alaska, but I was actually vacationing in India during this huge geomagnetic storm in May, and I was able to catch the aurora from northern India, which was just insane. So all around the world, people are spotting auroras, and it's really, really cool. As somebody who's been really passionate about aurora chasing in the Northern Lights for most of my life. I saw my first aurora when I was 4 years old and got really into this stuff in high school. It's really cool to share my passion for the aurora and to see other people witnessing what I saw when I was 4 years old. That really changed my life. But Okay, yeah. So first off, I'm going to show you this really cool video. So this is actually a loop in time. So at the very top of this sort of plot here, you can see the time just kind of stepping through. And what I did is there was this big geomagnetic storm on October 10th that reached a KP 8 out of 9. So KP is kind of how we measure global geomagnetic activity. It runs on a 0 to 9 scale, 9 being the highest, which corresponds to a G5 or extreme geomagnetic storm. A G4, which is what this storm was, is considered severe. So it didn't quite reach 9 out of 9. The one in May did, but this was a G4 KP8 geomagnetic storm, and auroras were seen all over the world. And I think this is really cool. One of my friends was scraping X, formerly Twitter, the social media platform, for aurora reports, and he plotted them on a Google map. So what I did is I took those data and I ran some code, and I created this little movie that shows how as night falls, starting, let's say, in Mongolia and China, and sweeps across Europe and then the Atlantic and then the US and Canada, you can see how many aurora reports come in, and you can just see how far south and how equator-ward the aurora was seen during this one event. So as scientists, as a scientist myself, I look at this and I say, this is really valuable information. You can see where the auroral ovals are. You can see how far south the aurora gets. And from that, you can get a lot of information about what is really going on physically in the entire system around the Earth, Earth's magnetic fields and things like that. But before I talk too much about that, I really want to kind of give you some context to what the aurora really is and how it ties into space weather. And, in the last point in my bottom line up front, that sort of yellow text you saw, my first slide, I said, it'd be really nice if you all could become space weather ambassadors and sort of aurora education ambassadors after this talk. And this is why, because not only are we seeing a lot of auroras around the world, aurora photography, aurora chasing's really at an all-time high in terms of popularity, but with that comes a lot of news articles that take advantage of the hype and scare people into thinking that space weather is this dangerous apocalyptic thing. And there's a lot of misinformation out there. So it's really important that people are educated and receive the right information so that, they're not scared of the aurora, but instead are wanting to see it for themselves. So what is the aurora? Well, it's nature's most spectacular light show. It's a piece of identity for many northern cultures. Up here in Alaska, there's many indigenous groups that hold the northern lights in high regard, and it's a significant part of their religion and knowledge systems. It's light emissions caused by charged particles from outer space, streaming along magnetic field lines, colliding with gases in our upper atmosphere. That's sort of the sciencey definition, and if that sounds like a foreign language, don't worry. I'll be explaining what that is in a sec. But most of all, and this is really important, and I think it's sometimes easy to forget if you're really delving into the science, and I definitely forget this sometimes when I'm doing all my classwork, but it's really captivating. It's mysterious, it's surprising, it's just exhilarating, and most of all, awe-inspiring. And it's something that when I saw the aurora for the first time really did change my life and change my perspective on what I wanted to do with my career. So everything is connected to the sun. The sun gives Earth energy. Of course, we have weather on the ground, like clouds and rain and wind, and the sun obviously gives us life and is why we're here. And the sun also gives us space weather and the aurora. So space weather refers to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. When somebody asks me what space weather is, instead of giving that sort of sciencey definition, I usually just say it's the aurora, because the aurora, as you'll learn here in the next 15 minutes, is the culmination of the sun-Earth connection. It's really the manifestation of all these processes going on the sun in interplanetary space. And then as that energy hits our magnetic shield and is sort of rattled around, the aurora is the final result. And I think it's the perfect embodiment of what space weather is. And it's what I always tell people when they ask, what does this really do? How can this affect me? And I say, well, have you ever seen the aurora borealis? That's space weather. But it's not just the aurora, of course. There's a whole slew of phenomena going on all at once in outer space. And it's really a diverse and exciting field to be a part of. You can see here on the left, you have shock waves, you have million-degree plasmas, in the sun's atmosphere, you have huge, giant magnets in space, huge, giant, strong magnetic fields. You have solar flares, you have tons of spacecraft measuring, plasma in different conditions and really extreme environments, right? Parker Solar Probe is the fastest human-made object ever created. human-made spacecraft ever created. You have coronal mass ejections, these huge explosions and clouds of plasma erupting off the sun's surface. Space weather is really, really cool, but a lot of people don't know what it is. So hopefully, by the end of this, you'll have a better appreciation for what space weather is. And if you don't understand the science, at least there's really cool movies you can watch too. So everything starts with the sun. The sun, as we all know, is made of gas and plasma. Astrophysically, it's actually a pretty ordinary type star. It's a G2 type star. It's composed of layers. So photosphere is sort of the sun's surface. It's the layer that we see when we look at the sun, even though you're not supposed to do that. And the corona is the outermost layer. It's the sun's atmosphere. It's what you see when the photosphere is blocked by the moon during a total solar eclipse. Because you're blocking that really bright disk of light, you're able to see the wispy corona that extends out from the sun and eventually flows into the solar wind. And the solar wind is kind of like if you imagine the sun as a hot cup of coffee, right? You have this liquid in your cup, which is really hot, and it's radiating steam off from the top. And this steam is kind of like the solar wind. It's just constantly radiating away from the sun and permeating throughout all of space, including, flowing around all the planets. And if those planets have magnetospheres and magnetic fields extending out into space, energy from the solar wind, these charged particles with magnetic fields can be transferred in and penetrate down through those magnetic fields, potentially into the planet's sort of near planetary space environment. The sun is magnetic. So like I was talking about the solar cycles, that's due to the sun's global magnetic field, which flips every 11 years. And in the process of flipping, there's a lot of these sort of knots of magnetism that form and bubble up and cause more space weather. So this magnetic field extends out into space with the solar wind and forms the interplanetary magnetic field. So not only are we being blasted by a bunch of charged particles from the sun and the solar wind, but we also have magnetic fields that are flowing around Earth as well. And I just talked about the solar cycle, but every 11 years, the sun sort of goes through this min-max period where you have a high season or kind of like a summer season on the sun, really active space weather where there's a lot of explosions, high-speed streams of solar wind, fast gusts of solar wind, big coronal mass ejections. And the sun is dynamic, right? It's a space weather. It's not space climate that we're talking about right now. Weather is dynamic. It happens every single day. It's changing by minutes, hours, and days. And now, just to add some context, right? When we look at the sun from the ground here on Earth, this is what it looks like, just sort of this unassuming ball of white light. But as soon as you put a telescope into space and put on a UV filter, put on those sunglasses, you're able to see the sun in different ways. So what you're seeing here in these sort of colored, these false color images is the sun's outer atmosphere, the corona. And by imaging the corona, you're able to image or better sense where the magnetic fields on the sun are. As you move outwards from the sun, from the surface out into space, that plasma and gas is no longer bound by gravity, but is instead bound by the magnetic forces within magnetic fields. So really bright regions in these images are really strong magnetic fields where the plasma is really hot. And then conversely, when you see these dark regions, you don't see too many in these photos. Those are called coronal holes. That's where the plasma is a little bit cooler and the magnetic fields just sort of loosely flow out into space. So here's just a cool movie, and I don't know, here we go. It'll play here. Just going to skip forward so you can see these really cool videos of the sun. Again, these are in those wavelengths I was just talking about, those ultraviolet wavelengths that are able to see the sun's magnetic fields. So you can see that the sun is not just this unassuming white ball of light that you see from the ground. There's a lot of things going on, when you put on some special sunglasses and you're able to see in different wavelengths, all what's sort of in the sun's atmosphere bubbling around. You have these huge ejections of plasma. It's honestly just beautiful. If not just scientifically amazing. Basically every single one of these events could be a whole thesis project for me, but don't want to think about that right now. But yeah, just an incredible star we have, just 93 million miles away. And a little bit closer to home, Earth produces its own magnetic field through the interactions of a solid and liquid iron core, which is many, many thousands of miles beneath our feet. This creates an intrinsic magnetic field. That's why our compasses work, and that extends. Doesn't just stop at the surface. It extends into the atmosphere, and then of course out into outer space. But it doesn't just extend, forever, right? There's this solar wind that exerts a pressure on the magnetic field, and as it weakens, as we go further away from the planet, that pressure equalizes, and we get sort of a shock front called a bow shock. and we get this sort of protective bubble that forms where the pressure from our own magnetic field meets the pressure from the solar wind and the charged particles in the magnetic field traveling along with the solar wind. And usually, this protective bubble, which we call the magnetosphere, is able to protect most of the space weather that comes from the sun. But when the solar wind is really fast and dense, these big gusts of solar wind from these ejections of plasma, and also just, more or less all the time, there's some energy that does leak through. So over our polar regions, just like a bar magnet, if you've ever done an experiment where you put iron filings on a piece of paper, hold the bar magnet underneath, you can trace out those field lines. Well, right over the north and south poles of Earth, you have these funnels where the particles from the solar wind can, through a process called magnetic reconnection, be funneled down over the poles. And that's why we get auroras in the polar regions. So the aurora is formed really by two, I would say, regimes of processes. You have large scale processes, so things on the global scale, things on the order of the entire Earth in terms of distance or radius. Then you have really, really small scale processes that are like chemical reactions that actually form the light that we see. So on large scales, you have solar wind that's coming in, right? Coming out from the sun and has a velocity and has a magnetic field. It has pressure, it has particles, and it then meets our magnetic shield, our magnetosphere. And a lot of it does just flow around. It's sort of diverted like a rock in a stream of water. So a lot of this flow of solar wind doesn't necessarily penetrate down through our magnetic shield and influence our Earth in the ways of aurora. But sometimes if the magnetic field in the solar wind is pointed south, so BZ south, you may have heard of this, Earth's magnetic field points north, BZ north. That's all the time. So if you're looking at Earth in outer space, the field actually goes out of the South Pole and flows north and then back through the North Pole, down through the Earth again. So when you have a north and a south, just like two bar magnets, and you bring them together, well, what happens? They kind of attract, right? So this attraction, this sort of transfer of energy is what happens at the shock front of Earth's magnetosphere, where the solar wind is coming in. And the energy from the solar wind can then couple and then flow down through those weak points over our poles and create auroral ovals, which we have one over the northern hemisphere, responsible for the aurora borealis, and one in the southern hemisphere, which is responsible for the aurora australis. And in these auroral ovals, aurora occurs every single day or night here. So here in Fairbanks, Alaska, where I'm located, we're right underneath the northern auroral oval, so I see aurora every single night, which is pretty awesome. Now on the small scales, charged particles, these charged particles, they get accelerated by field lines around Earth. So they're kind of bouncing around these magnetic field lines in Earth now that they penetrated in, and they're getting energized and energized and energized. And eventually they gain so much energy that they fall down and they penetrate our atmosphere. They have so much energy that they're able to overcome the magnetic field, and they're sort of raining down. So, like we have rain on Earth, on the ground, we also have rain in space. Called precipitation, in fact. That's the scientific word for it. So these molecules and electrons and protons, mostly electrons and protons, rain down into our atmosphere. And along the way, just kind of like a game of Plinko, they collide with gases in our own atmosphere, in our upper atmosphere called the ionosphere, which is mainly composed of O plus and N2 plus. And as these electrons from outer space are kind of guided by these magnetic field lines, they start interacting with our gases. And just like a neon lamp, certain sort of molecular transitions produce different colors that we see in the aurora. So when one of these electrons comes raining down, it'll first interact with O plus, which is above 200 kilometers here. And that interaction produces red light. Then as it goes down in altitude, it'll interact with nitrogen and oxygen, and sort of in combination that produces a green light. And then below 100 kilometers, we have nitrogen, which kind of glows this crimson or pink color. And if you've ever seen the aurora really dance, you'll notice that you get all these colors at once, especially this really bright, what's called a nitrogen fringe. So it should be noted that, the aurora occurs really in only these four colors. You have blue, red, green, and then this sort of pink-white color. So and really everything else that you see, all the different colors in between, are due to mixing of these four main colors. So now what happens when the sun gets really angry? I've been talking about things like coronal mass ejections and high-speed streams before. So let's get into this and really explain what happens when space weather becomes severe space weather. So, the sun is dynamic, right? We have space weather, we have things going on every single day. The solar wind happens all the time as well, but things on the sun can enhance the solar wind and cause these big gusts of solar wind, these big, ejections of plasma that can travel out into outer space and potentially interact with planets, you know, planets including our own Earth. So, solar flares. This is a GIF of a solar flare here. It's a big burst of light. So it's just electromagnetic radiation. It travels at the speed of light. So as soon as we see it here on the ground or see it in space with our satellites, it's already here. Now, these solar flares usually happen around active regions, so sunspot groups. So that's why, I was showing you that solar cycle graph earlier and the sunspots increasing. As we get towards solar maximum, we see more of these solar flares. And these solar flares, big bursts of energy can destabilize parts of the sun's corona, parts of the sun's atmosphere, and in the process blow them off from the sun and out into space, kind of like a cannon firing a cannonball out into space. Now, sometimes these CMEs, coronal mass ejections, that's what they're called, are directed towards Earth, and sometimes they're directed away from Earth. But we have instruments on board satellites called coronagraphs, which is what I'm circling here. It's this sort of red, this red instrument. Those are looking at the sun and creating artificial eclipses so we can see the ejecta coming off. So what you're seeing here is a big burst of energy, a big burst of plasma. So physically, these are particles, not light now, that are traveling out into outer space. So these may take anywhere from 1 to 3 days to get to Earth, whereas solar flares are seen in minutes. And I emphasize the difference between solar flares and CMEs because people often conflate them and they're not the same thing. So you might see a notification on your phone of a big solar flare, but a CME does not always have to occur with a solar flare, and vice versa. A CME may also occur without a solar flare causing it. So keep that in mind, but oftentimes they are linked together. And it should be noted as well that CMEs cause geomagnetic storms and cause aurora, and solar flares do not, right? We need some sort of enhancement in the solar wind. We have to have more particles, so higher density of particles, or those particles have to be traveling faster to see anything change in the solar wind. Light is not going to do that. So while we will see effects from solar flares, in other sort of technological systems, geomagnetic storms are primarily caused by CMEs and also coronal holes. So perfect segue. Coronal holes appear as dark patches in extreme ultraviolet images. So again, this is looking with those special sunglasses at the sun and seeing the sun in a different way, which exposes the magnetic fields which control the plasma at these altitudes. So what we're seeing here are these darker regions in extreme ultraviolet light that correspond to open field lines, which means that these particles are coming out from the sun and they're not trapped by anything. They can flow freely and at a higher rate of speed. So these fast solar wind streams flow out, and they're kind of like lighthouses because these coronal holes stay with the sun as the sun rotates every 27 days. So in fact, on the descending phases of solar cycles, it's very common to see these geomagnetic storms from coronal holes hit Earth every 27 days as the sun rotates through. So these coronal hole high-speed streams sort of are kind of like these lighthouses, kind of like a snowplow. They push slower particles in front of them and create this high density compression region. And then behind that or after that, in the perspective of the Earth, you see a high speed stream, which is really fast solar wind, usually lower density, and then things return to normal, as soon as that solar wind stream rotates out. So with all this being said, right, space weather not only gives us aurora, but it can also do some damage. And, this is something that is, obviously of importance, but you should know that it's not going to cause the next apocalypse. Likely not, I should say. Scientists never say it for sure about anything, but I'm pretty confident in saying that a Carrington class event, if you ever heard of a Carrington class event, is not going to plunge the Earth into the next Stone Age. But space weather does affect technology in outer space around Earth, in our atmosphere at high altitudes and latitudes, and on the ground in a lot of ways. And luckily, there's the Space Weather Prediction Center at NOAA in the U.S. There's space weather offices in Canada and in many other countries around the world that are constantly monitoring this activity on the sun and issuing watches, alerts, and warnings that power grid industries, aviation industries, and many other customers of these space weather alerts do pay attention to. So I actually just accepted this sort of, I guess, volunteer position on this Space Weather Advisory Group, which is a federal advisory committee that serves the White House here in the US. So I'm really excited because I'm going to be working on a lot of the applied side of space weather and how we can be more resilient as a country here in the US to space weather impacts. So now, just to touch briefly on the Carrington event, if you don't know about the Carrington event, this is probably the most infamous space weather event ever. So this happened in 1859. There was a large sunspot group on the sun observed by Richard Carrington, one of the first observations of one of these sunspots and a solar flare actually from one of these sunspot groups. So he was actually just looking at the sun, and it just so happened he observed what's called a white light flare. So usually these solar flares are measured on a scale from A to X, and they're measuring X-ray intensity. So we're usually looking at X-rays because although these solar flares look really bright in these extreme ultraviolet and X-ray, these extreme ultraviolet and X-ray images, they don't actually affect the total sort of radiative output of the sun in any major way. Like if there's a big solar flare, even during solar maximum, the actual brightness of the sun does not really change by more than, 0.003 of a percent. But during one of these big solar flares, like a super big solar flare, you can actually see it on the sun as white light, so you can see it from the ground. So Richard Carrington observed one of these white light flares, and then about a day later, there was one of the largest auroral storms, one of the largest sightings of aurora all around the world, almost to every single latitude and longitude that we've ever seen. So auroras were seen really as far south as the equator, and I guess as far north as the equator. And the energy in the ground from these currents, so there's aurora in the air and there's changing magnetic fields. And if you've taken a physics class, you might have heard of Maxwell's equations. Well, one of those equations basically states that if you have a time varying magnetic field, that induces a current. So you have currents in the ground as a result of these magnetic fields in the air, in the ionosphere, in the aurora. So there was so much current in the ground during the Carrington event that people operating telegraphs could unplug them and send messages without anything being plugged in. There was so much energy. And the sparks from, tapping the plates together to send the Morse code were so intense that they lit telegraph paper on fire near the operator, shocked them, and caused them to basically fall back in their seat. And many stations burned down in the US. So when people reference the Carrington event, people really reference the idea that, okay, what if that happened now? Because we have not seen a Carrington class event for about 60 or 70 years. It's not just, it really just hasn't been the Carrington event. There's been other big events as well. This one gets the most press, but we really haven't seen extreme space weather like this, affecting Earth since the 50s or 60s. So, the question is now, obviously there's more than telegraphs, so what would happen? And we don't know. We're just going to have to wait and see. So all this talk of geomagnetic storms, what actually happens with the aurora when one of these storms occurs? Well, you have more particles raining down into the atmosphere. You have the magnetic fields really kind of guiding these particles down. And as more energy from the solar wind flows and penetrates Earth's magnetic shield, the auroral ovals then expand as a result. So here's sort of the average auroral oval during quiet time. So again, there's always aurora somewhere on Earth, but during a geomagnetic storm, that auroral oval expands to lower latitudes. And here's my photo actually from the aurora I saw in India. It wasn't much, I'll tell you that, but it was there. So potentially my worst aurora photo I've ever seen, but arguably my most prized or most special aurora photo for me, at least. And of course, the questions are always, can you forecast the aurora and how can I see it? So let's kind of get into that. And this presentation is not really meant to be an aurora forecasting course. I have a lot of information on my website, which I'll have linked at the end. But if you want to see the aurora and if you want to forecast it, it's really hard. So, space weather and the way that we forecast space weather is about, I would say, at the maturity that we were at forecasting terrestrial weather in the 1970s. So we're really far behind, and that's not because, well, we don't really know what's going on scientifically, physically, in outer space that well, because it's just so complicated. But we also just don't have the measurements. We only have a few spacecraft monitoring the sun and monitoring the solar wind that's coming in. So we don't have that much information to base our forecasts off of, right? So there's really three tiers of forecasts, I would say. There's a 27-day forecast, which relies on the fact that coronal holes rotate around every 27 days, that lighthouse effect I was talking about. There's a 1 to 3 day forecast, which captures more of those transient events, those high-speed streams. After we see that high-speed stream and that coronal hole on the sun, we can have a better idea of when it's going to hit and how how severe it's going to be. And also these CMEs, of course, usually take around 1 to 3 days to reach Earth if they're directed toward us. And then there's a sort of hours to minutes is watching the solar wind pass spacecraft that are more upstream, that are outside of Earth's magnetic shield towards the sun. We have, we have three solar wind monitors at what's called Lagrange point one. So 150,000 miles, I want to say. I think it's 150,000 kilometers actually upstream of Earth. So between the sun and the Earth, that gives us about a 30 to 60 minute heads up of what's actually coming and what will eventually hit our magnetic shield, and whether or not that solar wind has the right magnetic configuration to couple with Earth's own magnetic field and transfer that energy down into the aurora. So here are some places to see the aurora. Of course, Fairbanks, Alaska, Tromsø, Norway, Abisko, Sweden, Finland, Iceland, Russia, places in Canada as well. I've been to Churchill, great spot to see the aurora, and Northwest Territories as well. I want to get to Yellowknife really, really bad. So it needs to be dark and it needs to be clear. So typically August to April is aurora chasing season for the northern latitudes. So here in Alaska, we start seeing, aurora tours popping up and starting to be ran in mid-August, and then we usually cut things off at the end of April because it just gets too bright. It needs to be clear. So spring months are typically the best, and that's reflected in the amount of tourists we see again. In Fairbanks, March is just insane. So I run a couple aurora photography workshops in March every single year just because I think this year I saw the aurora 21 out of 30 days in March, or 31 days in March. And yeah, that's pretty normal. And it really helps to be near the equinoxes. So that's why March is also a great time to travel to Alaska to see the aurora, because around the equinoxes, just due to Earth's rotational axis and the tilt of Earth relative to the sun and the incoming solar wind, there's something about that transfers more energy from the solar wind into the aurora. And scientists don't necessarily know, the real specifics on why this happens, but the actual effect, if you're interested, is called the Russell-McFerrin effect. And in terms of a moon phase, I'm preferential to a new moon, but really all moon phases are fine to see the aurora. It's not like the aurora disappears under a full moon. It's just harder sometimes to see those really faint displays. And here's how to take a photo of the aurora. Again, I have much more detailed information on my site, and you can always email me if you have specific questions about gear or processing or time lapse. But really, anything can do it now, and that's part of the real excitement of this solar cycle as well, is that we're experiencing solar maximum at a time where everyone essentially can take an aurora photo and use that photo and really upload that to social media and create this really awesome kind of cascade of reports coming in, which can help other people see the aurora in real time. So yeah, if you have anything newer than an iPhone, I think 10, you should have night mode, which can easily capture the aurora. Maybe not in the quality like this, but to some decent-ish degree. Helps when the aurora is a little bit brighter and when there's a full moon out for smartphone photography. Of course, if you have a DSLR mirrorless camera, you're in much better shape and you have more control over these things like shutter speed, aperture, and ISO. So, ISO can really vary, especially I've used values as low as 160 under a full moon here in Alaska. There's so much snow on the ground that, it's just so bright. It's just crazy. And then, of course, shooting raw and using a tripod is definitely recommended. So now let's transition to a different topic, but definitely in the same vein. So, I always say, like, if you just use those photography tips to take a photo of the aurora, well, you know that what you just did can be used for science. It's not just, you shouldn't just throw that image away. You should upload it to a place like Aurorasaurus that scientists can have access and collaborate with you to understand what the aurora is and how we can better forecast it. So citizen science, as a definition, is organized research in which members of the public engage in the processes of scientific investigations by asking questions, collecting data, and/or interpreting results. And just a quick note is that the terminology citizen is changing, but just for sort of familiarity's sake, I'm using the term citizen science, but a more, I guess, appropriate definition now is called participatory science, because of course you don't have to be in the US if you're trying to contribute to a US sort of founded project. And citizen science has many principles. I'm not going to read all of them here verbatim, but just highlighting what's in yellow here, and probably what's the most relevant for this crowd is that citizen science projects are built upon these principles. Citizen science is acting upon these principles, and one of those principles is reciprocity. So if you're a photographer giving a scientist your image or images, and your time and effort has been put into those photos, you should get something back for that, whether it's co-authorship on a publication, sharing in some scientific journal, or some sort of press. But just know that this is known. These sort of principles are known, and people should be following them. And I'm a photographer myself, and if somebody wants to use my photos, I'm totally fine with that, as long as they invite me to be on their paper, because it benefits me. And it's not easy to go aurora chasing sometimes. You have to drive hours and hours away and spend hundreds of dollars on gas and lost sleep. So just make sure that you're getting ample credit for the effort that you put into your photos. And citizen science, of course, is not just about the aurora. It's really this wide field that encompasses many different sort of topics and genres. So it's really heavily used in sort of the biology adjacent fields. There's actually a citizen science project called iNaturalist, which is, I think, the one pictured on the top left there, where people can download an app and then just take photos of the things in their natural environment, and then that gets uploaded to this database. And there's been some really cool scientific discoveries just from iNaturalist, like mapping species and seeing the effects of climate change on different species and flora and fauna and things like that. But of course, citizen science is really relevant for the astronomy community. A lot of web-based projects identifying galaxies and like wide field images and things like that. But then, of course, for auroras, citizen science has really cropped up recently as an important player in the way that we're doing scientific research. And some recent aurora citizen science discoveries are here. So these are all discoveries, all these auroras have been around for as long as auroras have existed. So as long as Earth has had a magnetic field and the solar wind has been blowing. But recently, aurora chasers have put forth their photos and contacted scientists saying, "Hey, what we're seeing is really weird. Can you help us out with this?" And because of that collaboration, we now have some weird auroral phenomena that may not even be aurora at all. So starting from the left here, we have Steve, or strong thermal emission velocity enhancement. We have fragmented aurora-like emissions. We have Ragda, red aurora with green diffuse arc, and we have auroral dunes. Steve is perhaps the most viral of these, citizen science discoveries. Now, it was first documented in 1911 by a scientist named Carl Stormer, who was doing work in sort of the Norway, Sweden, Finland area. And those results are published in Hunnecole McDonald 2020. So if you want to learn more about the historical context of Steve, I invite you to check out their paper there. But in 2018, citizen scientists started noticing Steve a bit more. And, especially the fact that this weird, quote unquote, aurora, or proton arc, as they were calling it, was appearing to the east and west instead of to the north, where the normal aurora is. On a normal night. So they started noticing this proton arc, and then scientists were visiting Calgary. So these were aurora chasers in the Alberta aurora chasers community. So scientists were visiting the university there in Alberta, and I think it was actually the University of Alberta, maybe not Calgary, but anyways, these aurora chasers went up to the scientists after they were actually giving a colloquium, and at a bar, they were looking at these images on the back of, really just on the back of these cameras, and just puzzling at what this thing was. Because the scientists, as soon as the aurora chaser said, "Oh, we're seeing this proton arc," the scientists said, "No, you can't see a proton aurora, because proton auroras are usually invisible." And yeah, the citizen scientists, these aurora chasers, showed them the images, and the scientists said, "Oh, that's something completely different. Like, we have no idea what that is." So in the meantime, while the scientists were scratching their heads about it, the aurora chasers decided to name it Steve. So then, of course, scientists came in and were like, "No, we can't call it Steve. Let's put a backronym to it." So they called it strong thermal emission velocity enhancement. And using the swarm satellites, so these low-flying satellites in low Earth orbit, they realize that there's this characteristic signature of Steve, which actually makes it potentially not even an aurora, because the way that it's produced may not be the same way that auroras are produced, and also the color is different too. You can see that Steve is mostly white and kind of pinkish, Well, auroras are not white, right? Auroras are four specific colors. So Steve is maybe not an aurora. It's like almost as if you had a really hot river of gas in the upper atmosphere and you heated it up so much that it was glowing white hot. It's like if you heat it's like if you heated up a metal really, really hot and it started glowing, it's sort of the same phenomenon. So potentially not even an aurora, but this discovery in 2018 really set off a chain of discoveries, and the family of Steve grew. Now we have friends of Steve. We have potentially Steve cousins or uncles. I think there's a high latitude Steve now. So Steve is typically observed at mid latitude, so south of the auroral oval in the northern hemisphere and north in the southern hemisphere. So during geomagnetic storms, especially, Steve is very prevalent. But now we have things like Ragda, red aurora with green diffuse arc. We have SAR arcs, which had been known about, long before Steve and relatively well documented. But with the help of citizen scientists, scientists realized that these SAR arcs can evolve into Steves. So you can see here in this bottom panel here, these two all sky images. The SAR arc is this very broad red emission here. And then over time, it actually narrowed and evolved into the Steve. So potentially there was this flow channel that narrowed and got really, really fast to the point where it could cause this sort of white hot color to form. And we have auroral dunes. And I'm definitely not an expert in lower atmospheric physics, but you have gravity waves that propagate up from the lower atmosphere to higher altitudes where the aurora is. So the aurora, again, is sort of 80 kilometers to even as high as 500 kilometers. But in this lower altitude range, you can get these gravity waves that sort of occupy the same space as the aurora, and then you get these weird kind of dune shelf, these dune sort of striations that form in the aurora, which is pretty cool. And these were discovered in 2020 by observers in Finland. And then finally, my favorite are fragmented aurora-like emissions, or FAEs. So these are relatively unknown. They're kind of like tic tacs, or like these little green blobs here that the red arrows are pointing to. And they appear very similar to what's called streaks that are associated with Steve's picket fence. So Steve is this sort of white arc or band that forms right after sort of the aurora gets really intense in what's called a substorm. And then usually what happens is this little picket fence, it literally looks like a picket fence of green emission forms right next to the Steve. And sometimes along this picket fence, like a messy exclamation point, you get this little streak that comes off the bottom of the picket in a really weird way, like a weird angle. And what's significant about that is that these pickets are usually field aligned, so they're aligned with the magnetic field. And that's how most auroras are. They're usually aligned with the magnetic field, and these big pillars or curtains. But these little pickets, these little streaks are very similar to the fragments in the way that they're not aligned. So they're kind of coming off at a weird angle. So maybe they might actually be generated locally within the atmosphere and not due to particles coming in from outer space at all, which is really interesting. So anyways, these FAEs are relatively unknown, and the fact that there's only been a couple papers posted about them recently, and just until a few months ago, we only had observations from places like Svalbard, Greenland, Antarctica for some reason, which is usually the hardest place to get photos of the aurora. But I posted just sort of a little informational tidbit on X about what FAEs were, and I just asked people kind of like out of the blue if they had any photos. And we got a really nice time-lapse video from this guy, not a scientist, on a ship in the Northwest Passage. And he's just running an all-sky camera, and he had some really awesome observations of FAEs. So it just goes to show you that people are really helping scientists and helping move the field forward through observing the aurora and submitting their photos. So how can you contribute? Well, the easiest way is to submit your reports of aurora and your photos to observing platforms like Aurorasaurus. So you can just go to aurorasaurus.org. And what Aurorasaurus is a NASA citizen science project. I actually interned with them in 2020, and their website is really focused on mapping out where the aurora can be seen in real time around the world. So you go to their website, you say, yes, I've seen the aurora, or of course, no, I haven't seen the aurora, and both yes and no are equally important to report. And those data are then plotted along a map with models of where the aurora should be seen according to fancy equations. And a lot of times those fancy equations don't work out, especially during big geomagnetic storms. So seeing the discrepancies in where the aurora is being seen versus the models is really scientifically interesting. So that's why we need your help to plot where the aurora is being seen. Of course, it also helps aurora chasers too, because if you know where the aurora is being seen, then you can maybe travel to one of those locations. Maybe there's somebody near you who's seen the aurora, and you can get a little report, a little alert on your phone. They have that set up as well. You can subscribe for alerts if there's a big cluster of reports in your area. That's really helpful for like urban centers where there could be hundreds of reports if there's a really big geomagnetic storm. But also, uploading your photos is super important too, and those data get made available to scientists. Of course, with the right permissions and sort of asking photographers, making sure it's okay to share those images as well. So, and if you're really interested, you can become an ambassador. You can become an Aurora Source ambassador to promote Aurora citizen science in your community. And there's a form online for that. And that's really great because you can sort of be this liaison between the science community. So the scientists present every single month sort of work that they're doing, which could benefit from citizen science observations and collaborations with Aurora chasers. And you can take that information and then share that with your own community and hopefully forge some really cool connections. There's tons of more citizen science projects here. This is just a quick screen grab of the NASA fleet of citizen science projects that are currently underway. And you can also directly collaborate with scientists as well. So if you have a really cool image sequence, or you have, an all-sky time lapse of fragmented aurora-like emissions from the Northwest Passage, definitely make a post online on Facebook, and scientists are always on those groups. So those aurora chasing Facebook groups. And, if you really want to make your data sort of science friendly, record accurate time and geolocation, record raw files without any edits, submit your data to online repositories. That's a good way to get found. And if you see something interesting, again, just make a post. You can even email scientists. Scientists are always keen to get photos from people. Everything's interesting. And of course, make sure you get credit. So just wrapping it all up here, we are in solar maximum, and we will keep seeing more amazing auroral events for years to come. This is a great time to be an aurora chaser. Excitement for aurora is at an all-time high, but also science awareness needs to match the hype. So, right now we're not seeing that. Of course, the aurora is being seen all over the world, but along with that, we're seeing all these news articles coming out saying the aurora is X or Y or Z, when really it's not any of those things. So, it's really a great time for people to step up. And now that you have all this information and you have me as a resource, right, feel free to email me, message me, whatever you want, if you have more questions. And if you get people who are interested in aurora science, so that we can really keep the narrative straight and let people know that what you're seeing in the sky is all tied back to space weather. And now is an excellent time to get people involved in citizen science. If you have photos of the aurora, make sure to upload those to Aurorasaurus. You can do backdated observations too. It doesn't just have to be in real time. And again, we need more space weather ambassadors who are passionate about the science, educated with the right science, and are able to bring science to the public. So you all can be space weather ambassadors. And I hope that was enough. And if we have any questions, I can take those now. But otherwise, my email's here. And then I actually have a little ebook that I created about the aurora. It's free. Just type in this link and it'll be sent to you automatically. And yeah, again, thank you so much.
So a little bit of a preamble, and you'll get why this matters to my question. My day job, I'm a systems engineer for Rutgers University. So I work in the networking field, and we maintain the university's wireless access points. And there's a lot, and we track all sorts of things like error rates, data, retransmissions, all the fun stuff like that. As a hobbyist, I'm also an amateur radio operator. And
Okay. Yep.
the space weather is very important to amateur radio, and in very sort of general terms, the solar maximum tends to make my amateur radio hobby better. But on the other hand, CMEs, we can track the error rates. They go way higher than they usually do in the wireless access points in the university. And knowing that really both are essentially radio waves, I'm very curious if you can maybe shed a little light on why this is generally good for my amateur radio, like de-expedition type stuff, but bad for my day job.
Yeah, I don't know a whole lot about. I need to get my amateur radio license. Actually, people have been pushing me to do that. I believe that solar max. So okay, during solar maximum, you have the sun's producing a lot more radio waves. So you have, and also just sort of waves in all sort of different spectrums. So you have X-rays, you have radio waves, gamma rays, all these different things. And when they reach Earth's atmosphere, because this is just light, so it passes right through our magnetic field. It ionizes a layer in our ionosphere called the D region or the D layer. And I think for your ham radio, for your radio transmissions you're using for your ham radio, those are the ones that need skywave propagation. So they need some sort of electrons to bounce off of and reach targets at longer distances. So when you have a thicker ionosphere during the daytime, which is during solar maximum, when you have more radiation coming in, ionizing that upper atmosphere, creating a larger sort of region of this enhanced electron density, that can better affect your propagation. So that can make your signals propagate further, and I assume probably with better clarity as well. So, of course, there's other things too, like solar flares and CMEs can negatively affect your transmission. But in terms of error rates and CMEs, that's interesting because I'm not, I guess if they're radio communications, I'm not sure what frequency that's at, but and whether or not it's just sort of like line of sight communication or what, but GPS is really affected by big geomagnetic storms. So actually a fun fact is that, well, not so fun actually, but during the May 10th event, the estimated economic impact from the GPS outages for the farming community in the US was $500 million of lost profits. So GPS can really do a number on those who rely upon it during geomagnetic storms like that.
As far as I could tell, from what I've learned in astronomy, the sun is considered a star, and it does, age into like a red
Yeah.
giant and such. Would that affect the difference of the solar weather if that time were to ever come, or can you use like the solar weather tracking to tell the age of our sun, or the age of another star, or the weather of another star? If we were to ever, analyze other stars and their solar flares and conditions?
Yeah, it's a super good question. So, yeah, I think, and yeah, I'm not super familiar with what the sun's. I mean, I know that the sun's going to go into this red giant phase and eventually cool off and form like a planetary nebula. I think is the most popular theory. But I think as the sun gets larger, it should rotate slower, right? Conservation of angular momentum, I would say. And if the sun's rotating slower, our solar cycles will be longer because the solar cycle period is directly related to the sun's rotation speed. So that's called the Rossby number. And stars have Rossby numbers, different Rossby numbers. The sun is actually kind of a weird one. You can find papers that go through, different stars that we've surveyed, and we've been able to measure their sort of angular rates of rotation. The sun is kind of in a weird no man's land, if you will, of Rossby numbers in correlation with other sort of solar flares and CMEs and things like that. So the sun is kind of a weird one, but yeah, other stars rotate quicker, which would typically mean shorter solar cycles and probably more severe space weather activity. I know that the Proxima system, there's some debate on whether or not life would even be possible on that planetary system because of all the space weather from one of those stars. I think it's Proxima B that is spitting off huge solar flares and CMEs that could potentially be strong enough to just strip away planets' atmospheres, or just totally, bake those planets in huge amounts of radiation. So, yeah, I mean, scientists look at planets with aurora, and especially exoplanets with aurora as potential, green flags for life being present. Because if there's an aurora, that means that there's a magnetic field in that planet, and that's potentially protecting it from the bulk of whatever stellar wind is coming out. So
When the sun gets mad, does it hit the earth?
yes, it does. Yes, when the sun gets mad, it does hit the earth with um, big explosions of gas and plasma, and usually can produce some really fun lights in the sky, but can sometimes um, give people headaches that are trying to do stuff with power lines and keep your home running. So, yeah, usually it's a good thing, but sometimes it can be bad.
You explained that there are solar cycles on a roughly 11-year basis, and that the
Yep.
cause of the solar cycles is a flipping of the sun's magnetic field.
Yeah.
Why does it flip?
Yeah, so I think that's still open for debate, honestly. I don't know personally why the sun's magnetic fields flip, but basically what happens is, well, so the sun has a magnetic field first of all, and because it's rotating and the sun rotates at different rates at different latitudes. So if you've ever, I don't know, they have these in some like science museums, but if you've ever taken a big ball of liquid and you start spinning it up, you'll notice that the poles don't really rotate at all, but then the equator is just spinning around really fast. So those magnetic fields are in some way bound to the surface of the sun. So as the sun's rotating, every 27 days, those magnetic fields at the poles versus at the equator are not moving at the same rate. So they start to sort of bunch up and they start to get warped and twisted. So it just so happens that, at some point, those basically that sort of warping and twisting reaches a like stress or like breaking point, and that's when we have these field lines popping out of the surface in sunspots in big active regions. And it's all a function of the rotation rate of the sun. I'm sure there's some fancy model that's done this, but the dynamo of the sun, which creates the magnetic field, is it operates on timescales roughly 11 years, which is all just due to the sun's rotation rate. So if the sun were rotating faster, then the solar cycle would be much shorter, and then of course conversely as well. So I'm not sure exactly why it flips, like physically, like the actual physical explanation, but phenomenologically speaking, it's because of the way that the sun rotates at different rates at different latitudes.
Thank you for the nice presentation. And I have two questions actually. In the one of
Hmm.
the first slides you showed,
Yep.
blue dots are those that represent the reports.
Yep.
Yeah. Why I don't see any from the southern hemisphere? Do Borealis and Australis occur at the same time? Or
Yeah. Yeah. So this is just like a sampling bias. So yeah, this is just surveyed from people on X. So I don't know if my friend's just not followed by a lot of people in the southern hemisphere or what, but Aurora Borealis and Aurora Australis occur at the same times. Although
right.
it should be noted that the Aurora Australis does not reach the tip of South America or the Horn of Africa, because the auroral oval at that hemisphere is tilted towards Australia and New Zealand and then away from these other continents. So it's the same reason why at the same latitudes in the US, it's really harder to see the aurora in Europe because the auroral oval is tilted towards North America. So even during the big storm in May, where there was a larger survey, you still only saw a few reports from South America and 10 reports from South Africa, but there were hundreds of reports from Australia and New Zealand because the auroral oval is tilted towards them.
Yeah, right now it's closer, southern hemisphere is closer to sun right now, right? Compared to
Yeah, so the geographic but the geographic and the geomagnetic poles are totally different. So the seasonality of the Earth relative to the sun, and yeah, like you were saying, doesn't really have any bearing on where the auroral ovals are. I mean, the auroral ovals haven't moved in the past, probably 60 to 100 years. There's been some papers comparing, but they've always been, or at least, in modern history, been tilted towards North America and tilted towards the sort of Australian and New Zealand areas.
yeah. Okay.
I have two questions.
Okay.
So, does the moon get affected by solar storms? That's number one. And number two, I know that Earth is like tilted in an angle. So, would the aurora borealis, the way we see them, would it be affected if it wasn't at a tilt?
Yes, really good questions. So, first question about the moon. The moon is really interesting because it's when it's rotating around. Okay, let me just go to one of these figures with the Earth's magnetosphere. So, yeah, let's just do this one. So, I'm not exactly sure where the moon is in this picture, but it's way down here. So, the moon is deep within Earth's magnetotail. So, sometimes it's protected by Earth's magnetosphere, and then other times, most of the time, actually, it's not. So when the Earth is on the day side and it's not protected at all, it's directly, in the line of fire from one of these big things, one of these big coronal mass ejections or big solar storms. So it's going to be a challenge if we want to settle on the moon, how we're going to deal with all the radiation. And then to your second point, or I should say second question, that's an interesting question because the tilt of the Earth kind of affects how well the solar wind and the energy from outer space is able to penetrate our own magnetic shield. And if it's tilted in one way versus another, it's hard. I personally can't say what would happen if the Earth wasn't tilted. Would our magnetic field be tilted like it is, or would it be the same? It's really interesting because Uranus, for example, is tilted, it's at like 70 degrees or something crazy, right? And its magnetic field is also tilted at a really weird angle too. So Uranus actually might not have auroral ovals, but might have like little auroral, I don't know, like spots, almost like freckles or something. And so that's really interesting to think about. And if our magnetic poles eventually flipped, which they probably will at some point, it's happened many, many times in history. During that process, we might have an auroral oval like over Mexico. We might have one over China. Who knows? Because our magnetic field is going to be really weird. So who knows what'll happen if that ever occurs. But in terms of the tilt of the Earth, like the actual physical tilt of the Earth and the geographic poles, it would just affect sort of how well the energy is able to penetrate in, I would say.
Thank you.
You mentioned there was I guess a satellite that detects space weather. And you mentioned an artificial eclipse. Are you able to speak to how it creates that artificial eclipse a little bit?
Yeah, of course. So this is the SOHO satellite. Can't remember what it stands for. Solar Observer, something like that. It's been around for like 30 years. So it's the SOHO satellite, and then this is the LASCO instrument on board SOHO, and you're looking at the C2 camera essentially. So there's two cameras. There's a C3, which is a blue version of this. It's just a little bit more zoomed out. And there's a C2, which is this more zoomed in version. And then this little white circle here is actually what the sun would look like if it was overlaid in the same image. And then this sort of darker, this solid circle around this white outline is what's called an occulting disk. So physically what's going on is there's a camera pointing at the sun, and then there's this little arm, this metal arm that's sticking out with a little disc attached to it that's blocking out the sun's light. And when you can do that, you can take a longer exposure and you can see more of that faint, wispy solar wind behind the sun that would otherwise be completely drowned out by the sun's intense light. So that's basically what's going on, is you're creating an artificial eclipse, just like you'd see it from the ground. On Earth, you can see the corona during a total solar eclipse here on Earth. You're seeing about the same thing in space, just all the time.
Thank you. Any other questions for Vincent?
Going back a moment to like the topic of making an artificial eclipse, is there a way you can make an artificial solar flare? Like, has someone ever attempted to make an artificial solar flare to do some research on them, or no?
That's a good question. I don't know of anybody who's tried to do it like in space and like really simulated it, because I guess the thing is too is like, it's so much energy. I don't know how you could actually do that, but there's certainly simulations of solar flares. And actually, I guess I can just, let's see, I'll just open up a new window here and I'll show you the D region absorption, this model called DRAP, which is something that the NOAA Space Weather Prediction Center, this is like an operational model. You can go to this website right now. It basically takes, if there's an enhancement in X-ray flux, which is due to a solar flare, it'll take that enhancement and then it'll model the effects on the ionosphere. So we actually have a radiation storm going on right now. I didn't really touch on radiation storms because they're not super relevant for auroras, but right now we have a radiation storm. So you're seeing the amount of signal absorption in the entire world. So areas that are, in sort of a more red shade are experiencing more signal absorption. So imagine if you shot up a signal at a certain frequency, how many decibels of signal power would be essentially absorbed by the ionosphere. So you can see the day-night terminator here. And then this little sort of blip was when there was a solar flare happening. This is probably yesterday. And then this is the radiation storm. So these affect the high latitudes and altitudes more than just the sunlit side of Earth. And then you can see that radiation storm getting a little bit stronger. And of course, there's more at the southern hemisphere right now because we're in winter in the northern hemisphere. So it's, you know, it's the people in the northern hemisphere are tilted away from the sun, so we're not seeing the effects as strongly. So this is something that's kind of interesting. It's not really an artificial solar flare per se, but you're taking the solar flare and you're making a simulation of what is supposed to be happening.
Okay, so could it be possible to create a future artificial solar flare for like predicting when solar flares would hit in certain locations, or?
Yeah, that could be a possibility. I think everything's on the table right now because I mean, that's always the goal is to predict when these things happen. So yeah.
Interesting. I was just asking because if we can make artificial eclipses, you know, to tell when eclipses are to occur, then certainly there must be a way we can create like artificial like solar weather like effects to predict when exactly a solar weather condition would occur.
Yeah. Yeah, I mean, what they do in like labs at different universities around the US is if they want to fly an instrument in space and measure the solar wind, they'll set it up in a special chamber and they'll pretty much simulate the solar wind. And you can kind of measure that and see how well the instruments perform. So,
Is the sun bigger
Then what?
than all the other solar system?
that's a good question. I think that the sun is actually kind of in the middle of the road. There are stars that are smaller and there are stars that are much, much larger than the sun.
Sounds like we're good with questions. Again, thank you so much for coming to speak to our club. Really do appreciate it. Having all the solar activity that we saw, even in New Jersey last month, it was a hot topic that we've heard from the group. And so really, really, again, appreciate you coming on and talking about it. So thank you.
Yeah, of course.